So they sent an email saying unauthorized access, and they pretend to be Google. I'm not sure how exactly. Maybe it was just like in the header, right? Um,
From
but yeah,
Godwell.com.
yeah. Okay. So, anyways, they called them pretending to be Google support, and there was a hacking attempt on the account, and they actually tricked this guy into giving them full access to the Google account, and in their Google account, I think in their drive or something, they had like their what's it called? Their seed phrase. So once they had that, they could just get into the wallet and take all their crypto. But yeah. All right. So that resulted in $3 million being stolen. I mean, wait, no, this is not 3 million. I can't read. Sorry, guys. I'm getting stage fright. So this is $300 million, and yeah, that's quite a lot of money. Can I get a fire emoji in chat if that's true?
It's like 9 zeros.
Tough crowd.
It's like 8 zeros.
Tough crowd. Okay. Anyways, so just like that, all the money's gone, and yeah. Now, if you guys were to do this, make sure your OPSEC is better. Don't spend it all and buy mansions. So, and also give me a cut if you guys ever try this out. Maybe Yoshi wants a cut too. But yeah. So don't buy Birkin bags for girls you don't know. Don't buy G-Wagons for girls you don't know. Don't buy mansions in Florida. Don't go to clubs and get bottle service with signs that have your real name on it or your usernames that you use on Discord to scam people. And yeah, that's basically it. That's how you not get caught. And maybe like go to a country that doesn't extradite to Canada or the US or wherever you're from. We are an international community, I think.
Yay.
All right. That's the talk. I think I'm over time by 1 minute. That was the pre-show. Thank you guys for coming out. Let's get into the reverse engineering now. I'll pass it over to my good friend and colleague Yoshiksi.
We can't start right now. We'll start in 9 minutes.
Okay.
We'll start in UFT time, yeah. So just wait for like 9 minutes, but I'm gonna screen share anyways. Yeah. We'll start in 10 though. Hi. There's a few snacks if any of you guys want them. It's just chips though.
Is it okay if I did an RSVP and just join in?
Yep.
And do you think it'll be fine if I've never like done CTF before? I just wanted to check it out.
Yeah,
Pretty
pretty much.
Okay.
It should be for a beginner. I don't think the room's gonna fill up all the way. So, yeah. Hey, how loud is my mic for the Discord people? I don't think I can turn it up. Um, okay. Uh, okay, it's good if it's sensitive, I guess. You can just turn me down whenever. I got like a really cheap a cheap mic from my a cheap microphone from a hackathon, and it was made in China. Oh yeah, crisp. I'll turn that on. Yeah, I think it's better now. Nice, nice, nice. Okay. We'll just start in 4 minutes. Okay. So I think we can start now. It's 10 minutes after. So thank you guys for coming to the first UofTCTF seminar of the year. It's about reverse code engineering. So this is about the process of taking a compiled binary and trying to reverse it to find the source code or any secrets in a binary. So I'll show this. I'll show a few announcements. So there is another workshop that's happening later in October about physical security. So this is about lockpicking and RFID cloning and forcible entry. So if you're interested, there's a sign-up form somewhere in the Discord. It's in the announcements channel. We just want to gauge how many people want to come, and it's also going to be hosted by the DEF CON people, so the DEF CON Security Village. There's also a few CTFs that we're going to play this week. We don't know what they are right now, but if you want to join us when they happen, you can join us through the CTF bots that we have. You just need to verify in the Discord. So I'm going to provide a little bit of structure about what's going to happen today. So the first thing we're going to be doing is we're going to be learning how code is actually forward engineered. So this is how CPUs work, how operating systems work, how operating systems run code, how code is compiled. And then the latter half of today is going to be the more practical segment. So this is actually taking apart code with decompilers and disassemblers. We're going to be using some debuggers today. We're going to be talking about obfuscation and also symbolic execution. So I'm going to get started and talk about CPU architecture stuff. So if you're going to communicate with your CPU, you need to have some protocols to talk to it. So this is what the instruction set architecture is. And the instruction set architecture is essentially the contract between a programmer and your CPU. So it defines how you would write code to your CPU with the allowed opcodes. It defines registers, which we'll get into in a bit. And it also talks about the word size, which is the standard size for all data that the CPU allows. So a few common instruction set architectures is the x86 architecture, which is in most computers. And there's also the ARM architecture, which is in most newer computers. It's in Apple computers and also Windows computers that use Qualcomm. So x86 is kind of old, and it's also kind of bad because it is made backwards compatible with, so it just supports so many instructions, and it's a lot of the instructions you're not going to use. So ARM is actually one of the newer standards that is part of something called RISC, which is a reduced instruction set. And these are ISAs that have a minimal number of instructions because you don't need that many for your CPU. So registers are the small storage units inside your CPU, and you're going to use these for temporary operations or if you're accessing any data from the RAM. So in terms of actual storage, your computer has the RAM, has a hard drive, and it has CPU cache, and it has registers. So the memory, the registers in your CPU, they have to be very fast. So they were called SRAM chips, and they're a more expensive type of storage that's specifically used for fast access and fast writes. And you're going to be using registers in your CPU to calculate pretty much anything. Everything in your CPU will work with registers. Any data that's being manipulated will be stored in registers. And you'll see a bit of this when we actually get into the assembly part. But if you're manipulating any data, it has to be stored in a register. It has to be modified register-wise. And yeah, pretty much that. So there are different sizes for registers. And we actually give a name for every register. So in your CPU, there might be several registers. In x86 ISAs, you have a few registers. You have RAX, RBX, RCX, so on and so forth. There's actually a few, like 30, I guess, around 30 registers. So they're given different bit sizes, so you can actually talk to a specific bit segment of a register. For 64-bit processors, you can access RAX, which is the register that contains all of the 64 bits, or you can address the lower half with EAX, and in the lower half with AX, and so on and so forth. Every register is given a purpose. So for RAX is usually used for accumulation, or sometimes for functions as the return value, and passing arguments to functions. But sometimes you'll also see it just used as general purpose register. So maybe for some part of a calculation, you just use REX. Other registers have a very set purpose, like RSP, which is usually used for the stack pointer, which we'll get into later on. But sometimes you'll see it used general purpose as well. Usually when you see RSP being modified, you get some sort of indicator of what's going on in the program, because it usually is only used when a stack is being manipulated. Okay, then we're going to talk about the actual meat of a CPU, which is in the opcodes. So opcodes are bytes, a series of bits that is fed into the CPU, and parts of the bit stream are mapped to actual hardware components in the CPU. So usually opcode is represented in hex because you don't want to write all of the binary out. So we represent it as hex, and we don't actually read it as hex, we read it as assembly, which is the human readable version of an opcode. So these specific opcodes are on the left and the assembly is on the right. So the human readable version, it's not actually code. So as a result, you get different standards for assembly. You have an Intel standard, which is widely used. It's pretty much preferred if you're doing reversing, but there's also the AT&T syntax for assembly. And these are just different formats, right? Because assembly is human readable, so it's not actually understandable by the computer. Most people pick Intel though. I think GDB by default makes you use AT&T, but you can just set it to Intel later. And yeah, so that's the main difference. Assembly is not the same as opcodes. Opcodes are what the computer understands, and assembly is what is supposed to be understood by humans. So we're going to go over an example of how assembly can be executed. Now we have 3 instructions here, 3 assembly instructions. And the first one is going to be modifying 2 registers. So in total, this program is going to be modifying 3 registers. It's going to be modifying EIP, which is the register that is supposed to represent the instruction pointer. So inside a CPU, every time you load a program, the program is converted into a series of instructions, and the instruction pointer will point to the current instruction that should be ran. So if you look at EIP, it's pointing to the first line of my thing, which is 0x8049,000. So this is the first instruction. And what we're going to be doing in this instruction is we're going to be moving free into EAX. So essentially what this is doing is it's setting the value of EAX, which is our register, used as a general purpose register here, and it's going to be set to free. So I'll go to the next slide, and you can see that EIP changed in value. So EIP is now the next line, and in this line we are setting the value of EBX to 4. And the last line here, we are doing an add operation, and we're adding EBX to EAX. And the result of that is going to be an EAX. So EAX is the sum. It's going to store the sum. That's just how the instruction is designed. So that was a brief run through assembly, and there's going to be more assembly later on when we get to the debugging segment. But I hope you understand that most of assembly, when you actually see it, it's just modifying registers, or it's doing some specific calls. And most of the time, you'll be memorizing most of these instructions if you do enough reversing. So this may seem like very arbitrary to you right now, but once you remember the instructions, there's only a set few of instructions that you need to memorize anyways. But yeah, that is kind of a hurdle early on if you want to get started with this, is memorizing the instructions. So let's go into how code is actually turned into assembly, because we don't want to read assembly all the time. So there are two main tools for how we can actually run code. So the first thing is a compiler, and a compiler is a piece of software that converts source code into machine code. Or not necessarily machine code, it can also turn it into a general lower level representation of itself. But it converts it into a file that sits on your computer, and it doesn't run, right? You need something else to run it. And that's what an interpreter does. So an interpreter, oftentimes, it can take your high-level code and run it, or it can take your low-level code and run it as well. So interpreters are the actual software that executes the code. So we're going to go over some examples of compilers. So these are examples of compilers. You can have a compiler that converts a high-level code into another high-level code. An example of this is TypeScript, which converts its own language back into JavaScript. Then you have the classic compilers, which are ahead-of-time compilers, and these are used in languages like C or C++. And essentially, they just convert your source code into object code that just sits as a file on your computer. And you have this third one, which is kind of compilation, but it's kind of used quite often with interpreters at the same time. It's called the just-in-time compiler. And essentially what it does is it looks at your code while it's running an interpreter. It looks at the code. There's a analyzing routine that would analyze code segments that are repeatedly ran, and it would try to compile that segment of your code so that subsequent iterations are actually more optimized. So usually it makes the interpreter much faster, but sometimes if it picks a bad optimization, it can actually make it slower. But there are a whole set of processes to revert an optimization as well, which is called de-optimizing. And it's kind of its own beast. So you'll see it used in interpreters, like mainly with interpreters. The JVM has segments of this. The WebAssembly engine also has a just-in-time compiler as well. So sometimes compilers, or ahead-of-time compilers primarily, they compile down into something called intermediate representation. So they don't always compile down into machine code. Usually, most compilers these days want to be able to work with other compilers. So they convert into what's called an intermediate representation, which is a representation between the high-level source code and the machine code. And a common intermediate representation is called LLVM. It's used in languages like C++ and I think Rust, I'm not sure, but it's used in a lot of languages. And it allows code to compile into LLVM, and in something else that can actually run LLVM or convert that LLVM into machine code will be able to do so as well. So it allows for code that works between multiple languages, and anything that can work with LLVM would just be able to use the same tooling. So no matter what compiler, you have the same set of tools available underneath. And sometimes it also enforces its own optimizations. So it's much easier if you compile down to an intermediate representation, because if you write your compiler optimizations yourself, it's kind of difficult. So usually you want to use LLVM to handle the optimizations for you. Then you have interpreters. So there's only two that are worth mentioning here. There is a specific type of interpreter called the VM, And a VM interpreter is an interpreter that will take your source code and convert it into something called bytecode. So you can think of bytecode as like a sort of intermediate representation, but it's meant to be executed. So intermediate representation is not usually meant to be executed, it's meant to be compiled later on, but bytecode is an intermediate representation that is meant to be executed. And if you've looked at some JavaScript, if you've ever used, no, not JavaScript, but like Java, if you've ever compiled Java, you get a class file, and when you open a class file, you see Java bytecode. So the bytecode VM is a sort of software that reads the bytecode and can just run it directly line by line as a sort of VM, I guess. It just executes it directly. The next one you have is an AST interpreter, and this essentially converts your code into an AST tree, which is a tree about all the expressions in your program, which is a nice representation of your program because it can be parsed very easily when it's in a tree diagram. So you would be using post-order traversal to navigate through the AST tree and executing all the nodes in that. Some languages like Ruby use an AST tree as well. So these are interpreters that you'll see. Now, an interpreter and a compiler, they're usually parts of a larger toolchain. So this is an example of the GCC toolchain. It uses, well, it has several steps before it actually converts to a final compiled code. For C, you have a few things that need to be C specific, and that would be resolved by a preprocessor. So in C, there are things called macros, which are essentially little quick snippets that actually mean something else. So the preprocessor would actually resolve the macros and replace them with the expressions that they are supposed to represent. And it would also do something that is including the libraries from the headers. The compiler would take that preprocessed code and convert it into something low level. So maybe it's an IR or maybe it's the actual machine code. Once you have the lower level version, use an assembler to convert it into machine code. And after you have the machine code file on your computer, you do something called a linker. And a linker is, there are several versions of a linker, but the main purpose of a linker is to resolve different imports. So if you have several files that depend on other files, the linker is the tool to connect them all and make sure that the program runs as expected when it has dependencies. So there are two ways of linking, and the first way is called static linking. So static linking is when you take one of your dependencies and you just insert it at the top of your final executable. So if I'm grabbing some sort of function from standard library, I will just include that function somewhere in my code. So this is obviously not that great because one of the things is that your file is going to be very large. And one of the other things is that you'd be using versions that are probably not that secure. So you'd be using code that is already compiled, so you can't really reference and have it be updated very easily. So it's not that optimal. The other way is called dynamic linking, which is what most compilers actually do. And this is the process of adding a reference to the actual function and putting that somewhere in your code. So if I'm referencing malloc, I will just have a reference in my program, and the actual, when the program is actually being ran, my CPU would jump to the address where malloc is defined in, and it would just continue like it was part of the code, but it would just jump to where malloc is. So linking is pretty important because you're going to see it quite a lot. If you ever see your code just jumping to somewhere else halfway through, it's usually dynamic linking. So one thing that is pretty important, especially for game hacking, is the idea of a DLL. So a DLL is an alternate evolution path, kind of. Whenever you take a compiler, you can either compile to an executable or a library. And structurally, they are pretty much the same, except for one caveat, which is the DLL cannot be ran, it must be imported. So essentially, it's a collection of exports for other files. It's just a library that has to be imported by other files. So I have a DLL, it's kernel 32 DLL, it's a standard DLL for Windows operating systems. And you can see that all of the function definitions are all exports. So this program's actually included, this DLL is included inside of another program that I opened in a debugger. So yeah, this is a Windows debugger called X32debug, and you would just be able to see all DLLs, and all DLLs would just have exports. So yeah. So an important idea when you are working with files is the notion of a file format. So data is stored on your computer, but it needs to have a specific format or a specific standard for programs to actually read it and execute it. So these are like some common formats that you might know. For executables, there are a few that are worth mentioning. The PE file format is used for Windows, and it's used for executables and DLLs. So this is the file format for any sort of program that runs on Windows. There's also the ULF format, which is usually on Linux, and these are for executable codes and also libraries. So if you want to do any malware analysis, understanding the PE format is actually kind of important. The PE format is kind of your first way into a file. So if you're analyzing something, the PE format contains a lot of very good metadata. There is the header section and a collection of sections below it. The header area contains a lot of metadata about the program. There's some parts about backwards compatibility at the top in the DOS header and the NT header. And this is because Windows likes to make things backwards compatible. Usually you're not going to worry about this unless you want to make some tool that is matching files for if it's a Windows executable or not. Because if a program has these headers, the DOS header and NT header, usually it's going to be a Windows program. The next thing you have is a collection of, or it's like a map. It's a map of sections. So at the very top you have a map of sections, and you can see the size of every section. And what a section is kind of a region of your program designated for a specific task. So the most important section is the text section, and a text section contains all of your assembly code, all of your opcodes essentially. So that's all of the instructions in your program. It's going to be in the text section. There's also going to be a data section. So the data section is going to contain code or sort of constants that are already executed, and you can search for it. Maybe there are compiled strings or like some data structures that are already included, and there is constant values that you can look at. Pretty important as well, because sometimes the compiler will include a few strings like the compiler name, the version of it. So you can take a look here as well. You can run the strings command. The strings command is pretty good for finding some hard-coded values. There's also, for Windows specific, there's a resource, which I'm pretty sure it just stores like resources like images and audio. And there's a lot more. I didn't include them because there's no space, but there are a lot more sections. There's like one for imports, like function imports, and there's one for uninitialized constant data. And there's quite a lot. So you can spend like a whole evening reading for the PE file formats. It goes pretty in depth. But I kind of explained this, but yeah, it is really important. If you just want a cursory glance into a file, just look at the PE headers. You can learn a lot. Imports are really important. If you can see what the program is importing, you get a general idea of what it can actually do. If it's importing a lot of weird imports, like maybe it wants to set the execution of a certain part of its memory, then it's probably doing something not so good. If it wants to set something in a registry, it probably also is not that good. but these things vary. But just looking at the imports gives you a general idea of what the program can actually do. You can look at these section sizes. So the section, if it's very small, but the program can actually do a lot, the text section, I mean, if the text section is very small, but the program can actually do a lot, it might be an indicator that the program is actually packed. And we'll explain what packing is later on, but usually it's not a good sign. You can also check the CPU type and obviously the sections. So if you want to see the file format, you can use a Linux command. It's called file. I have 3 files that I installed off the internet, and all of them have different file formats. One of them is just raw data. One of them is a Windows PE32 executable, so it runs on 32-bit Windows and 64-bit. And I also have an ELF, which is it runs on Linux. So there is something interesting that you might see when you actually open up a file in some sort of disassembler, and that is the fact that it has addresses. But it has addresses, but it's not loaded on disk. So how does it actually have addresses? Well, the important thing is that even if a program is not loaded, it still wants a way to talk about addresses. So how it actually does this is it uses something called a base address, which it assumes. It assumes that the OS will load it at the base address. That's its preferred address. And if it has that base address, then all subsequent addresses will be an offset from that base address. So that's what relative virtual addressing is. You can see it here. If I open Binary Ninja, you can just see that all of my instructions have an address at the side, but they're not the real address, they're just a virtual address. And when you actually load your program, you're going to get a different address. Most tools, most disassemblers have something called rebasing, which is changing your base offset to a offset that you actually choose. So instead of the base offset 0x4000000, I can rebase it and give it a different address, and usually that makes it more aligned with the actual program that I'm running. So that's just something that you might see. So where is the program actually loaded? Well, we actually don't know when the program is loaded because of something called address space layout randomization. So this is a security feature in the operating system that makes it so that every time you load a program, the base address of the program is determined randomly. And why is this a thing? Well, it's because if you are trying to break a program through means like binary exploitation, it makes binary exploitation a lot harder because you don't know where the program is actually being loaded every single time. You can't assume that the addresses in your exploit are going to be the same every single time. So for binary exploiters, they have to actually leak a lot of things as a result of this. So I ran this program 2 times, and you can see on the underlined section that the addresses are completely different. And yeah. I'll actually take a look if Discord is. I think it's streaming, yeah. I think Discord is fine. Okay. So now this is an image that's kind of important. And you guys can, I don't know, we'll come back to this later, but this is pretty important. So when a program is loaded into RAM, this is the structure of what is on the RAM. So you are going to take the code and the data section from your file format. If you remember the PE file format, I'll just go back to that. The PE file format, it had a text section and it had a data section. So if we're going back, the text section is the code section and the data section is the data section, and that's mapped to the RAM somewhere, right? So that's going to be on the RAM somewhere. And we also give the program a stack and a heap. So these are 2 things that are given to the program. So we'll talk about the stack. So these are 2 new things, the stack. The stack, if you come from Like a non-OS backgrounds, you might know a stack as like some data structure that you can push values to and pop values to. But on the operating system, it is a form of memory given to a program that's usually 1 megabyte to 8 megabytes large. On Windows, it's 1 megabyte. On Linux, it varies up to 8 megabytes. It is used to store variables for a current function, so local variables in a current function. And the scope of what it stores, because it's actually 1 megabyte large, it's not going to use the entire width of 1 megabyte. It's going to want to limit its scope to 2 pointers. The 2 pointers are the stack pointer and a base pointer. So the stack pointer indicates the top of the stack, and the base pointer indicates the base of the stack. So stack pointer is RSP, and base pointer is RBP. So if you notice something, the stack pointer is at a lower address than the base pointer. And this is just a quirk of the stack. And it's a fact that the stack will actually move towards lower addresses. So we're going to look at a push example that actually increases the stack. When I push a value to the stack, which is essentially I'm adding data to the stack that I can use later on, I am going to subtract the stack pointer to make it actually go to a lower address. And this is just what they call the stack grows downwards, because the stack is growing towards lower addresses. So in this example, I'm going to be pushing a value, 0xEE, and 0xEE is about I think it's two bytes. No, 1 byte. Okay, I don't know, but essentially the stack pointer is decremented by the size of the data that I'm pushing onto the stack. So I would subtract the RSP. So the new RSP is 0x399C, and I would be storing the value 0xEE. So that's the process of pushing to the stack. I subtract the stack pointer by the size of my data, and then I store the value of my data onto wherever the stack pointer is pointing. The next operation I can do is popping from the stack, and popping is essentially removing data from the stack, while also taking the previously removed data and storing it locally so you have access to it. So what I do here is I just add to RSP, so essentially I delete that value, and before this I would actually take the value and store it into register, but after that I would just add to RSP. So that's essentially removing a value from the stack. We don't have access to it anymore. So you might have noticed that RSP and RBP, the area between it is kind of important. So as a convention, all of the data that we access is between RSP and RBP, and sometimes below RBP as well, above RBP as well sometimes. So we only work with this limited scope of data for functions, right? This little 2-pointer structure here, it defines the variables inside our function. So if we were inside a function, a lot of variables would be in between these 2 pointers. So I think, okay, there's going to be some examples later on, but essentially if you're going to be pushing local variables in a function, it's going to be in between these 2 segments. It's going to be below RSP and above RBP. So when we actually run functions, we are going to have a convention for calling them. And this convention will define how functions will manipulate arguments and how they manipulate the stack. So the first calling convention that we're going to be talking about is standard call. And the way standard call works is that if a function is going to call another function, then it's going to push all of the arguments that it wants to send onto the stack. So that's the first thing it does. Then it calls that function that it wants to call. And when it calls, it pushes RIP. And if you remember what RIP is the instruction pointer. So essentially, it's pushing the previous instruction that it wants to return to it's pushing that onto the stack. Then it's pushing RBP, and it pushes RBP because after it calls this function, it wants to restore the previous stack frame. So it's pushing RBP, so it knows the previous RBP value. Then it's going to allocate space onto the stack by a set amount for local variables and maybe save registers, but usually local variables. Then it does the logic, and once it's finished the logic, it deallocates the stack space, and it would pop RBP, and then it would just return to the previous function. So RBP is restored, and a few of the arguments that were previously on the stack are also deleted. So it's good to have a diagram of this. So we actually have a diagram, and you can see that the caller frame, the caller is responsible for pushing the arguments on. So the arguments are going to be from the first argument to the final argument. It pushes in this order, so it pushes the last argument first, and then it pushes the first argument last, because that's just a convention for this one. And it also pushes the RIP, which is the return address. And once you're in the function, you're in the current frame, you're in the function, you would have access to the old EBP, or the old RBP, and the variables for the current function. So one thing you'll notice about this is that all of the arguments are being pushed onto the stack. But the next calling convention is going to push a few arguments onto the stack. So the next calling convention is called fast call. And fast call is a calling convention that would push a few arguments through registers instead. So this is why it's called fast. The reason that we want to use registers is because registers are closer to the CPU, and they're made of SRAM chips, which are more expensive chips memory-wise. They're much faster to access, so we want to use them whenever possible. So we use 2 registers as arguments. And after that, everything is pretty much the same. If you have more than 2 arguments, you push all of the other arguments onto the stack. So this is what it looks like. It's pretty much the same thing, but the arguments are not all on the stack. It's only the third argument that's on the stack, and all subsequent arguments, they'll just be on the stack. So if you have 2 arguments, there's nothing on the stack. I forgot to mention that these 2, so fast call and standard call, these are for Windows. The next one is going to be for Linux. So the next one is going to be for Linux. And this is the standard one for Linux. It's mostly the same. There might be like different details here, but the main takeaway is that it would push 6 arguments through registers. So 6 arguments are passed through registers. If you have more than them, then they're just going to be pushed onto the stack. So the arguments are pushed onto the stack at argument 7 and so on. So those are calling conventions, and it's good to know calling conventions whenever you actually encounter them, because you get some sort of inclination that maybe if something's being pushed through the stack or registers are taking on weird values before a call, usually those registers are going to be taken away later and accessed relative to RBP or RSP. So yeah, it's important to know the calling conventions, so when you actually see it in assembly, you can know what's going on. And there's one more thing that is kind of important, which is how data is accessed. So this is kind of weird when I first saw it, but data in the data section, I'll actually circle back a bit. It's going to be at the front a bit, so it's actually kind of far, but when you load a program into RAM, right, you get this area, you get this structure, right, when a program's loaded into RAM. You have the instructions in a code segment, so that's where our program is going to be at. That's where RIP is going to be at. So remember, RIP is pointing to somewhere in this code section, but you also get data below it. So data is right below it. Now, modern computers, they have very large RAM, right? So my computer has like 16 gigabytes of RAM. Not all of it is going to be used for my not all of the RAM is going to be used for my program. but that's like 16 gigabytes. So if I actually want to access a value, I would be better off using a RIP, which is pretty close to where my data is, and adding an offset to it. Because there's a limitation if I just want to use the actual address directly, it won't fit in a single instruction. So I'd be better off just adding to RIP, which is relatively close to where the data is in terms of the actual address. I'd just be adding to RIP and I would just get the data inside the data section. So this is why you'll sometimes see RIP plus some sort of numbers. This is just what it's doing. It's accessing some constant that is in the data section. So yeah. And there's one more trick that I couldn't really find anywhere to put it, so I just put it here. You'll see when you actually load a program that data is stored in reverse order. And this is just any data that's stored in a memory for Windows and for Linux programs as well. Data is stored in reverse order. It's called a little endian. So when we read data, we read it as big endian usually. As humans, we read it as big endian. But for memory actually likes to store it in reverse order, so little endian. And it does this because it's easier for the CPU to calculate different arithmetic operations when the data is in reverse order. So if you see data in reverse order, don't get freaked out. This is just how it's stored, and you can just reverse it yourself if you want to get the if you want to understand the data. Okay, so we covered everything for forward engineering, and we can just take a break. The next half of this is going to be reverse engineering. So if you want to do stuff in a break, you can download this stuff. But yeah, we'll take a break now. 10-minute break. So yeah.
You want to check if the stage on Discord is started?
I think it is. Yeah, I'm pretty sure it is.
People can see, but I think like doesn't say started, so I have to click something.
Oh, I have no clue.
You have to click,
Oh, I see.
just don't uncheck that.
Okay, thanks. Okay, this mic is still on. Okay. Also, if anyone just came, there's snacks on the table if you want any. Again in 1 minute. Okay, so I think we can start back. The second half of this is going to be reversing. So we're going to cover decompilers first, and we're going to go into debuggers. So the debugger segment is the stuff that you just installed. If you can install it, it should be fine because, well, we'll just cover it like for the slides. Like I don't have a debugger here as well because I'm just running it on Windows. We'll also go through obfuscation and symbolic execution. So arguably the thing that you're going to be using the most is your decompiler and disassembler tool. This is probably your best friend when it comes to reversing, and there are a few tools that are mostly recommended. There's Ghidra, which is the free one, and it kind of gives a bad decompilation most of the time, but there's a very good plugin ecosystem. So sometimes you're still going to be using Ghidra. And there's Binja and Hexphrase. These are their own decompiler engines, and they're also kind of bad, but they're better than the other ones. They're the best we have, essentially. So if you don't know what a decompiler is, essentially it's a piece of software that converts machine code back into source code. But it's not the actual source code because it doesn't compile. It's pseudo source code. It's human readable source code. So how it actually does this is with a very convoluted process that nobody really understands, and you actually don't really need to know this, but it's kind of important if you want to understand some of the terminology that the decompiler actually uses. So like from a conceptual level, it's kind of beneficial, but you're never going to use this as practical knowledge, I don't think. So how a program is actually decompiled is kind of difficult because a program is packed up into this small bundle of machine code. You want to get as much information as you can. So what you're going to do first is you're going to read the file for metadata. So that would just be parsing the PE file structure or the ELF file structure, just checking the metadata like that. Then you would try to disassemble the program. So convert the machine code into assembly. Then you take that assembly and you try to convert it back into an IR. Then you take the IR and you try to find procedures, which are like functions. After you find functions, you try to get the control flow of every single function. And you use several other steps, like resolving types and finishing the expressions. So that is just the last step, but there's not enough space, so we just grouped it into one step. But the last step, there's a few more steps after that. That would just be involved in reconstructing the expressions. And what you get as a result kind of looks like source code, but it's not compilable. It's just used for the human. And a lot of the times it has a lot of errors. So a lot of times it's actually wrong. So the file reader is, yeah, a program that will read as much as it can. So you can actually read a lot, like as mentioned with the PE headers and the PE sections, you can actually know a lot about a binary without actually looking at the instructions. You can find the global variables, the functions that are imported, the names of the imported functions, and the start of the instructions, like the entry point of the program. Then you go for a disassembler, and a disassembler is a tool that mostly is 100% accurate. What it attempts to do is convert opcodes back into assembly, but sometimes it also makes mistakes. So sometimes it doesn't classify certain instructions as instructions. Sometimes it classifies it as like raw data. There are cases where instructions are very similar or not widely used, or they might be encrypted of some degree, and they don't show up as instructions that can be disassembled. So these are like some errors. With the tools like Binary Ninja and Ghidra and IDA, you have the option to actually go to the decompiler to say, reanalyze this part because this part is actually instructions, it's not data. And sometimes that would fix it, sometimes that would make it actually better. Then you have this process of IR lifting. I don't think this is an accurate image, but usually what it's supposed to do is it's supposed to take your assembly and convert it into an IR. And once it's made for an IR, it's a lot easier for a decompiler engine to analyze and create the sort of different things that is required for decompiling. So VexIR is an example of an IR that can be lifted pretty easily. It's used in Anger and a few other things as well. You can also lift it to LLVM. That might be beneficial in some cases. So that's a process. That's a step in a process to make it more readable for the decompiler. Then you have a step in a process which is finding procedures. So this is just finding functions. How you can actually find functions is through instructions that are associated with functions like jumps, calls, and manipulations of the stack with pushes and pops. Then you have this step of generating the control flow. So you want to map out the control flow, and what you do is you find basic blocks. And the definition of a basic block, as simple as possible, is a contiguous block of code that has one entry point and one exit points. So it doesn't branch off into anywhere. You chain together the basic blocks to generate a graph of how the program navigates the control. So yeah, you essentially turn programs that are line by line, like procedural, into a sort of graph. And the last parts that I kind of jumbled together is just the parts that are recovering the expressions. So you recover the types, you simplify conditionals, you create the loops that are taken from the control flow graph. You can like check loops for that if a basic block returns back to itself at some point. You can also generate functions from the procedure finder, and you can convert registers to variables. If enough evidence supports that, it should be converted to a variable if it's accessed enough times. Okay, so now we can talk about debugging, and you're going to be using a debugger a lot because some binaries you can't just analyze through a disassembler. Sometimes they are very obfuscated, and sometimes it's better to use a debugger to confirm your suspicions. If you have an idea that a binary is doing something specific, you can use a debugger to confirm those suspicions. So debuggers come in a few classes. There's userland debuggers, which are debuggers for programs, general programs on your computer. You can use X32debug, which is a Windows debugger, or GDB, which is a Linux debugger. And there are also debuggers that work at the kernel level. So WinDebug is a debugger that works at the kernel level. You'd be using this to debug firmware, drivers, and OS-specific software. So usually we use GDB. If you're doing CTF-Rev, a lot of binaries are compiled for ELF, so you're going to be using GDB a lot. GDB is pretty good, and you can learn it in probably one day. So GDB has a few specific things that it can do. You could step to, before I explain what it's able to do, a debugger is essentially a program that manipulates a flag in a CPU so that every single instruction is not executed immediately. Instead, it's executed line by line. So that's what a debugger does. It peers into a program and it executes it instruction by instruction. So instead of running the entire program, you can just see what happens after you execute specific instructions. So GDB, you have a few things that you can do with it. You can step to the next instruction. So if you're at a current instruction, you can step to the next instruction and see what happens. If you are at the instruction that would enter a function, which is a call instruction, you can step into that function, so you can go into the instructions inside that function. If you don't do this, you'll just skip past the function. So you want to step into the function if you want to do that. You can print local information like local variables. You can examine memory information. So anywhere in that segment of where the program's loaded into memory, if you remember that image with the stack, the heap, the code, and the data, when the program's loaded into memory, you can print any of that out. As long as it's reserved for the program, you can print any of that out with examine. You can set a breakpoint for a current instruction. You can set a watch point, but I think a watch point is mainly used for kernel debuggers, so it never worked for me. But you can do that if you want to check for when a variable changes, and you can use continue, which would continue until the next breakpoints. So you're going to be using breakpoints and continues if you have loops or if you want to reach a specific function. Yeah, so we're going to go over an example. If you downloaded Pondabug and you downloaded a binary, Pondabug is essentially an extension to GDB. GDB has a config file, and Pondabug is just like piping a lot of configs into the config file of GDB. And it's really good because GDB doesn't have, well, GDB has a UI, but it's kind of bad. So Pondabug is just a better UI of GDB. Every time you run a program, you get like a very nice view of all the registers, the stack, and yeah, and like CPU flags. So we're gonna debug the program. This is the program. This C code has some syntax errors, but the actual program that you installed probably shouldn't. It should probably run, I think. I'm pretty sure it runs, but the idea of this is that we are sending a argument in the command line. So the second argument that we send is presumably the flag, and we just check line character by character if the second argument that we send is equal to flag secrets. So that's our flag. We're checking the second argument is equal to that. And if it is, then we just enter the win function. If it's not, then we just exit out the program. So you can see the compilation command that I have at the bottom, and I'll talk about it in the next few sections. If you see there's a strip command, that's kind of important. So when I do GDB, my program, so I have my program locally and I run the command GDB, and I specify that I want to debug the program after I compiled it, so my program, you'll see a little warning at the top that says no debugging symbols found. So what does this mean? Well, when you compile a program, you have the option of adding debug symbols. And this is just adding a whole lot of symbols. Usually it includes the actual source code of the program as well. So you could just use it whenever you're building your program to have a better experience debugging it. Instead of going line by line through every assembly instruction, you can actually go line by line through your code's instructions. So every line of your C code, you could do that. So it's pretty good. But our compiler command, it didn't have the -g. So it didn't have the -g, it didn't have -g, so we don't have any debug symbols in this. But that's okay. There's another thing that we usually do when we have a program, and that is we want to try to enter the main function. But in this case, we did something weird in our compilation command, which was stripping it. So when you strip a binary, all of the default symbols, all the default exports are gone. Usually this results in a program that is smaller in size, but it's kind of bad for us if we're trying to reverse it because then we don't have any idea where main is. But this is generally okay because there are a few ways to get around this. So this is from Live Overflow, which is like it's like a general security creator, but like he has this method where he starts the program. So he goes to the first instruction of the program and he runs it. And then what he does, so that's the start I instruction. Start I starts the program and it breaks the first instruction. Once it does this, the program is loaded into RAM. So we actually have an address for the program is loaded into RAM. So what we can do is we could try to find the entry point now that we have the program in RAM. We have the entry point here. So we're going to type info files and we're going to get a list of things and we get the entry point. So this entry point address is important for us. We're going to copy the entry point address. And once we copy the entry point address, this is what we can do. We can use the X command, which is examine, and we're going to examine 16 instructions. So X/16i would print out 16 instructions from the address of our entry points. So whatever address that was copied, you can just put that instead of 0x555, so on. and you're going to see 16 instructions. So these are the 16 instructions right after our entry points. And there's one thing that is important that you'll see in most C programs is that at the very start, there is going to be a call to a function called libc_start_main. And this is an any C program. The call to libc_start_main will take one argument, and that argument is going to be the address of our main function. And if we look at the top, a few lines at the top, what we're actually doing is we are passing some value, some constant value, RIP plus some constant, which is somewhere in our some address, somewhere in our RAM. This is the main address of our program. So we're storing that into RDI, and then what we're doing is we're calling libc_start_main, and we're passing that argument through the register. So that's why it's an RDI. So there's a comment that PwnDebug has here, which is the actual address, and I've underlined it in orange. And if you missed any parts, like there's actually slides on the Discord if you want to backtrace. This is kind of rushed, and I'm just doing this for the slides. But if you want to trace back, there are slides on Discord if you want. Anyways, but yeah. So we have this address, and this is our main address, so we're going to copy it. It's in a comment, but you can just view it if you want. So we have the main address, we're going to copy it, and we're going to set a breakpoint at it. So how you set a breakpoint is you have the breakpoint, then you're dereferencing the address, so you would set a breakpoint at that specific address. So if you want to see all of your breakpoints that you set, just type info break, and you get a list of all the breakpoints that you previously set in your program. Now, if you remember what a breakpoint does, it essentially makes it so that if you run your program would stop at that breakpoint address. So I'm going to do continue just to check if we made it to the exact place. And this is pretty standard. So this is assembly that you're seeing right here. This is pretty standard for entering any user code, right? Any user code would kind of look like this. There's not a lot of weird commands. There's not a lot of weird instructions. These are all standard instructions like moves and subs and pushes and pops. So yeah. So there's an issue here that when I ran the program, I did start I. And start I ran it, but it didn't run it with arguments. And if you remember how our program is designed to take an argument and compare it with a flag secret. So we actually need to run this with an argument. So we're going to run it again, and we're going to run it with our arguments. In this case, we're just going to send the winning argument, which is flag secret. So that is going to be the argument. And when we run, we're going to reach the breakpoint. So we're inside main now. So now I can actually talk about this code. What is it actually doing? So the first few segments of this code, it is pretty standard when you enter a function. Whenever you enter a function, you're going to do some of these things. Maybe some of them are omitted, but usually you're going to be pushing RBP at some point. You're going to be moving the stack pointer back to the base pointer. So essentially, you are setting the stack pointer to the base pointer. So the stack is essentially 0 because there's no difference between them. So the stack is essentially cleared out. There's nothing on it. Then you're going to be pushing some arguments that you got previously. So that's push RBX. Then you're going to be subtracting some values from RSP. Presumably, you're subtracting it so that you allocate some space onto the stack that you're going to be using for variables later on. Now, when you work with variables, local variables on a stack, you would usually add some offset to RBP. So yeah, so this stuff at the bottom here, it is moving local variables. By adding an offset to RBP, you see move double word pointer RBP minus 0x37. It's moving EDI into the stack. So it's moving EDI into the pointer into wherever RBP minus 0x35 is pointing. 34 is pointing. So you're moving these register values onto the stack so that it's accessible locally. Then you're doing something after that, which is called a stack canary. Now, if you've done any binary exploitation, you know what a stack canary is, but if you haven't, it's a security feature that prevents buffer overflows. So sometimes when you have a program that doesn't check the input size, you can overwrite the values of other variables. And the stack canary is designed such that you have a random value in your stack somewhere, and if something overwrites that random value, then you have a check at the end, and if it is overwritten, then you know that somebody overwrote something else. So at that point, you can know that stack smashing happens, and you can just exit the program because there's some malicious activity going on here. So that's what the stack canary is. How experienced binary exploiters get around this is they leak the stack canary, and then they overwrite that stack canary with the stack canary that is expected, but then they overwrite the other parts with their evil values. So that's a way to bypass the stack canary, but you'll just see these things, and that's just what it is. It might look arbitrary, but that's just what it is. And you're doing something, you're setting AX to 0. Then we're going to go down a few times. So we're going to do next instruction, next instruction, next instruction, which is NI. So you can just do that a few times. You can spam it. If you don't want to spam it, you can just use enter on your keyboard because that saves the last command. But you're going down, so you're going down a few instructions. And let's explain what this is doing. So you have XOR, EAX, EAX. So you're setting EAX to 0, which is good. And what you're doing later is you are going to be storing a string constant into the stack. So you're storing this large number here at the side. That is all characters. So that's all characters. That's how a string be represented. And you're pushing that onto the stack somewhere. So you're moving absolute RAX, these large numbers, you are moving RAX into the stack somewhere, so it's storing it as a local variable. And then you're doing the same thing at the bottom, and you're storing it like right beside it. So essentially this is a contiguous block. It's one string, but we stored it 2 times because the string was kind of large. So we had to do it 2 times. And then you enter a for loop, and the for loop would be initialized here. So you actually don't enter a for loop, but you set the variable I equals to 0. I is not a register, I is on a stack. So we would be accessing the variable I from the stack later on. So there's a jump down here, and once we enter the jump, we would be entering the loop. So this is the loop, and what ends up happening in this loop is we take the value of I, which is on a stack, and we're storing it into a register. And then what we're doing is we're checking if current I is equal to the string length of my flag. If it is equal, then we're going to, well, if it's less than, then we're going to jump below. So that's what JB is at the bottom here. If you look at where JB is, below to compare, if RAX is smaller than string length, so if I is smaller than the string length, then we are going to jump back to the top of the loop. If it's not, then we're going to continue down at the bottom. So the call instruction at the bottom, that is the end of the loop. But if we are still in the loop, then we're going to do the jump below, and we are going to enter the loop, and we're going to be trapped for as many times until I is equal to string length. So our goal is to enter this call area here. So when you are navigating loops, it's kind of good to have a breakpoint set up so that you don't have to spam next instruction like several times. So we're going to set a breakpoint at the compare here. So just take the address, you can see the address on the side of the instruction, 0x5, or whatever it is on your end. You can set a breakpoint at that instruction, and then just like list your breakpoints if you want a refresher on the breakpoints that you set. We only set 2 so far. And we can continue. So once we set a breakpoint, this is where the loop is. It's going to be comparing every time, right? It's going to be comparing I with the string length every single time in the loop. So we're just going to continue about 13 times. Every time we do continue, we stop at the breakpoint. We do it about 13 times, which is like the size of our string. At the end of it, the loop is over. We are going to be able to do ni a few times. And once we do ni a few times, we're at the call. So at this call, we're going to enter the win function. Now, when I do this, I want to step inside because I'm calling a function. I want to step inside of the function. So I don't want to go to the next instruction. I want to step inside of the function. So I do si. And this is pretty straightforward stuff. This is not a difficult function. You have the basic function setup, which is clearing, which is pushing RBP and then resetting. Well, actually, you don't have any local variables, so you don't actually have to reset the stack. And next thing is you are going to move a string into some local variable, and you're going to move some arguments into a register, and the register is going to be used as an argument for printf. So that's just printing out correct, and then at the very end you are returning back to main. So this is pretty much where the program ends. If you continue on, then you're going to return out of the main function and you're going to be in a program loader, and then you're going to be calling exits. So that was kind of fast. If you want, you could look back over it to see what we're doing, but that's pretty much how you debug a program. You would just be reading the assembly, you'd be using these few commands, next instruction, step inside, breakpoint, continue, and you would be examining things sometimes. But yeah, this is just how you trace through a program. And yeah, so that's just an example of what you could do with GDB. So now we're going to move on to obfuscation. And this is another thing that is more theoretical. You're going to see it sometimes though when you are actually reviewing the code of a program. So there's a few types of obfuscation. There's source code obfuscation, there's compiled code obfuscation, and then there's packers. Technically, packers are not obfuscation, but they're pretty close enough to obfuscation because they make the code unreadable, so we would kind of count it as obfuscation, but they're kind of their own thing. So source code obfuscation is the process of taking your source code and making it unreadable for people. So what you can do is you can change variable names, you can insert code that is completely meaningless, you can have conditional statements that are absolutely difficult to work with. You can put code in eval. So eval is this thing derived from Lisp, which is essentially you have some expression and it's in like some sort of string, and you can just interpret that expression as part of the code. So maybe in Python you have the string x equals 2, and that's in a string. If you run eval on that string, it would just it would actually run the code x equals 2. So it's just evaluating strings as expressions. So this is kind of confusing for reversers if they're actually looking at this, because eval, you don't really want to work with eval. And you can also encrypt literals. So that's another thing that you can do. Now, it's kind of weird, right? Because you're not really supposed to share your source code in most things. Most of the time, you're sharing your actual compiled binary. So why even have source code obfuscation? Well, in some cases, you actually have to share your source code or segments of your source code. So if you've developed on a web before, you have JavaScript, and in some cases, you're going to have to give your JavaScript to your client because that's how it works, right? Maybe you have some captcha system that would have to run on the client system. So you don't want someone to read your source code because then they can easily find the algorithm that you're using and just find ways to bypass it. So this is why you want to use source code level obfuscation. .NET also has like sort of the same problem. Some of the parts in the bytecode are visible to the client, so you're going to try to want to obfuscate .NET as well. So these are a few tools. There's a lot more tools. You can make your own tools, but these are some general tools that will just destroy your programs and make it unreadable. Now there's binary obfuscation. So once you compile your program, you can do a few things to make actually looking at your program kind of difficult through a disassembler. So you can encrypt literals. This is a classic one. Just make your literals impossible to understand. because you're encrypting it, and you decrypt it sometime later in your program so that it can just be used directly. You also have this technique called function pointers, and a function pointer is a way to call a function for a pointer instead. So instead of calling malloc, you call the address of malloc, and that would just be the same thing as calling it. So you would do this by using a function to generate a function pointer. So you call this function and it generates a function pointer, and it would call the function for you. So if I have, for example, this function that I want to call virtual alloc, which is the Windows version of malloc, I would be generating it with a trampoline. So I'd be generating the function pointer of virtual alloc with a trampoline function, and a trampoline function would also call virtual alloc. So from a disassembler point of view, the disassembler, it can't run any code. It can only see what's happening. So it can't compute the function pointer. So it doesn't know what function is being called. So that's why function pointers exist, and it's very suspicious if you ever see any of this. Here's another thing is control flow obfuscation. So you have a function. Instead of one function, you have smaller functions that each do some specific part, usually some meaningless part, like maybe adding 1 to a number, and you just have several small functions, and it just makes it really much of a headache for the reverser. They don't want to navigate through that many functions. It's just a pain in the ass. Okay, and one more thing is very long and very weird expressions. This is mixed Boolean arithmetic. It is the process of converting expressions into a series of arithmetic and Boolean operations. So I don't know what this value is, but it's probably like 2 or something if you actually compute it out. But the value 2 here, it's being thrown through so many expressions that it's just kind of hard to analyze. You have to run the code. And what makes it even worse is this could be part of a larger expression. You could have sort of data in here that is not known beforehand. And if you have data here that's not known beforehand, you can't compute it directly, right? The disassembler can't compute it because it doesn't know what some of the data in here actually is. So it's just really, it's kind of hard. Like there's research to try to fix this, but yeah, it's kind of a pain. So there's packers. Now packers are really important because most things you're going to see now, most malware is going to be packed to some degree. So packers are a piece of software that converts your software into a smaller version of itself that has a piece of program that will unpack it. So maybe an example is if you want to reduce the size of your program, you could use Huffman encoding, and you compress your program into a smaller version of itself. And then at the very top of your program, you would have a function that uncompresses your program so that it would actually have the original data, but it would just be, unrecognizable if you're looking at it without running it. So there are a few types of packers. There's a few tools available. So there's UPX, which is Ultimate Packer, and this is kind of used for, it's not really that good. It's not really secure, but you could encrypt your data. It's usually used for compressing your program. Like that's the main selling point, is you can compress your program, and then when you actually run it, the UPX engine decrypts your program. So it's not that secure because they provide their own tool to unpack it as well. But that's just one of them. The other one is VM Protect, and VM Protect is kind of cool because what it does is it converts your program, all parts of your program, it converts it into bytecode. So once it creates a bytecode representation of your program is now entirely data. And you have an interpreter at the top of your program that would run your program as interpreted program. So the thing about this is that it generates a random bytecode for every single program and generates a custom interpreter for every program. So you don't have the bytecode, so you don't have the methods to know what the VM is doing beforehand. So every time you work with VM Protect, you have to analyze it without any help. The decompilers and the disassemblers, the decompilers, they're only trained off of known assembly and known bytecodes. But if the bytecode is generated on the fly, then you can't use your decompilers because they won't have any knowledge of this bytecode. So that's kind of cool. And Famida is pretty much the same. It has like a VM-based packing like VMP. It also has a lot of extra features like checking if you're using a debugger, so it just stops the program. It also encrypts your code, and it will obfuscate its imports as well. So we're almost done. This is one of the last things is symbolic execution. So symbolic execution is this weird thing. It came from theoretical computer science, but now it has real adoption. Usually you're going to think of it as a series of mathematical problems. So you are converting your program into a series of mathematical equations that you want to try to solve. So there are two things that are important here. There's the notion of a constraint. So a constraint is a specific condition imposed on a variable. So for example, one constraint might be that x has to be bigger than 5, or x times 4 needs to be equal to 20, or y minus 3 needs to be bigger than or equal to 6. So these are specific constraints on variables. Now these variables have the special property, which is having a value that is symbolic. So the value of these variables is not known beforehand, but they have to be solved. So the value of these variables will have to be solved so that they satisfy these constraints. They can be different data types. Usually they're integers or real numbers. Sometimes they can be bit vectors, which are essentially a series of bits. So the idea behind this is that you try to set up a sort of equation consisting of constraints and symbolic variables, and you use something called an SMT, and you try to solve it. So you try to solve for the values of your symbolic variables from a given equation. So what you actually do is you set up a tree of specific equations and specific paths. So if x plus y is bigger than 5, you would go down into these paths. If it's not, then you would go into some sort of basic block, and that's not the sort of result that you want. You want to try to reach the solution where you satisfy all of the constraints. So this is what an SMT solver does. It tries to find the values of the variables that will satisfy these constraints. And in this case, there are quite a lot of values for x and y that make this true. Like x equals 1, y equals 5, x equals 1, y equals 6. There are so many. The SMT solver just picks one of these and gives it to you. So there are a few tools that you can actually use if you have any SMTs. You can use zfree, which is used for direct SMTs. So if you have like a few equations that you want to solve and you want to find the variables that make it true, you can use zfree. It's pretty simple, and you're not going to use it for some of the larger programs. What you're going to use instead is you're going to use Anger, and Anger is pretty smart because it would take your binary and it would gather constraints from it. And essentially, it would have understanding of your program. What you can do is you can give it like an address for some specific function and tell it to just find what sort of inputs would allow me to reach this function, and it will just solve it for you. So it's pretty much magic. So we're going to go through one example of symbolic execution. This is a C code that would take an input of 5, so it's 5 bytes, but it's only checking the first 4 bytes. And you can see that there are a lot of if statements. There are a crap ton of if statements, and it's kind of a pain if you want to try to solve it by hand. So we're trying to find the input that would satisfy all of these if conditions, and once we find that, we would get the output winner So we can solve this with Z-free, and the process of creating a Z-free program is to import the Z-free library in Python, create a solver object, and then add all of your symbolic variables. So in this case, we would have 4 symbolic variables for the 4 bytes of our inputs, and we would set them up as bit vectors, which are the most versatile type, essentially. If we were working with integers, we would use integers, but bit vectors are kind of good because you can use Boolean operations as well as arithmetic operations. And then what we do is we add all of the constraints that we got from the file. So these are the exact same constraints that we got from the file. We just add them to our solver. And then at the very end, we check if there's actually a solution to our solver. So we check if it's satisfiable. And if it is, then we print out the values that it found that would make it satisfiable. So at the very end, I run my program and I get that the correct input would be flag full 4G. That's the correct input to my program. So that's pretty much all that we needed to cover today. It was kind of fast, but if you want to find more stuff, then yeah, there's stuff on UofTCTF org. So yeah, that's pretty much all we need to cover today. If you're interested in learning more about reversing, these are some other topics that you can look into in your own time. And we have a few resources at the end of the slides, so we're going to be posting the slides. And you can just go through them if you want in your own time, but these are also things that included into the slides. So thank you, everyone. Yeah.